Let's just jump right into this. I want you to picture a fortress, but, not a medieval castle made of stone. We're talking about an electric vehicle traction inverter. And this thing, it is operating under a relentless, extreme physical assault every single second your EV is out there on the road. I'm talking massive thermal spikes, violent high-frequency vibrations, blindingly fast electrical noise. So in this explainer today, we're going to unpack the absolutely incredible engineering it takes to keep this fortress standing, specifically focusing on the gate drive and the undervoltage lockout, or UVLO, safety systems.
So, consider this high-stakes question. How do you stop an EV inverter from completely self-destructing in just 2 microseconds? To put that into perspective, that is thousands of times faster than the blink of an eye. Because when we're dealing with high-power silicon carbide components, 2 microseconds is literally all it takes for a momentary voltage drop to cause a component to overheat, melt down, and just fail. The speed of these catastrophic failures is honestly mind-bending, and that is exactly why the safety systems we're about to look at are so absolutely crucial.
Here is our roadmap for today's explainer. 1. The invisible assault. 2. The active shield. 3. Architecting the fortress. 4. Zero-tolerance forging. And finally, 5. The ultimate siege. Okay, Section 1. The invisible assault. Let's look at the root causes of failure. Before we get into the specific threats, we really need to understand the main defense mechanism at the heart of this whole thing. It's called UVLO, which stands for undervoltage lockout. Think of UVLO as this highly critical hardware safety switch. When the supply voltage drops too low, the system simply doesn't have enough charge to fully turn on the power transistors. In that state, it is incredibly dangerous. It causes massive resistance and a ton of heat. So UVLO steps in and forces an immediate hard shutdown to prevent the power modules from literally burning themselves alive.
Right, so what actually causes that dangerous voltage drop in the first place? Well, the source material gives us 4 primary physical root causes. First up, auxiliary power sag. Just imagine the car's 12-volt battery momentarily choking under a really heavy load, dropping down to 6 volts for just 20 milliseconds. That essentially starves the gate drive. Second is ground bounce. The extreme switching speed of these power components creates intense electrical noise, and that noise can actually flip the logic signals in the system. Third, mechanical harmonics. You can think of this as an invisible earthquake. Frequencies between 100 and 1000 Hertz from the motor can actually match the natural resonance of the circuit board, shaking the solder joints until they form microcracks. And fourth, desat, or desaturation interference. That same crazy electrical noise we just talked about can accidentally charge up safety capacitors, tricking the whole system into thinking there's a short circuit when there really isn't one, which leads to a totally unexpected loss of power.
Moving on to Section 2, the active shield. We're looking at software and hardware defense mechanisms here.
Now check out the dramatic contrast in reaction times here. In the automotive world, the highest functional safety standard, which is called ASIL D, requires a software response within 60 milliseconds. Now to you and me, that's incredibly fast. But to a silicon carbide transistor, 60 milliseconds is a lifetime. It's way too slow. That's why software just isn't enough for these faults. Instead, the hardware's safety management unit steps in and physically locks out the signals in under 100 microseconds. It completely bypasses the software just to save the hardware.
But here's the crazy part. Even 100 microseconds isn't the fastest line of defense. Remember UVLO? When the positive gate supply voltage drops down to that critical threshold of 13.5 volts, the dedicated driver chip executes a hardware self-lock in 1 microsecond. 1 microsecond. That is an extreme microscopic level of speed. It instantly forces the gate closed and flags a fault pin, physically severing the path to destruction before the main processor even realizes what's going on.
So once that microsecond hardware block kicks in, the system needs a safe place to land, right? It actually degrades gracefully based on how fast the car is moving. If the motor is spinning at high speeds, we're talking over 7,200 RPM, simply opening the circuit is super dangerous because the motor acts like a massive generator, pushing out lethal voltage. So it uses what's called a stepwise active short circuit. It safely shorts the motor coils to clamp the bus voltage securely below 720 volts, but at low speeds, under 2,000 RPM, the system safely cuts the power entirely. It enters an active open circuit, which just lets the motor smoothly freewheel to a stop, keeping the car totally controllable for the driver.
Section 3. Architecting the fortress. How design prevents these issues before they even start.
All right, so how do we stop those 4 invisible attackers at the gate?
To beat the power sag, engineers spec out these high-end LLC capacitors that can physically hold the required voltage for 20 milliseconds, letting the system ride out the power drop. To beat the electrical noise, they use an active Miller clamp, which is essentially a ridiculously fast-acting electronic brake, along with robust isolation chips rated to block massive voltage spikes of over 100 kilovolts per microsecond. Plus, they don't just turn the gate off at 0 volts. They inject a negative 5-volt bias, forcefully slamming the electronic doors shut and locking it. And what about those invisible mechanical earthquakes? They dynamically tune the physical circuit board structure. They add rigid metal reinforcements to guarantee its natural frequency stays far, far away from that 100 to 1000 Hz danger zone.
The material science happening here is absolutely fascinating. To guarantee these safety circuits don't get thrown off by wild temperature swings or microscopic vibrations, the design strictly locks in the use of Class 1 COG capacitors. And yes, I know that sounds like a droid from Star Wars, but these components are incredible. Made with calcium zirconate, they have basically a zero temperature coefficient. That means the performance doesn't change whether it's negative 55 or a blistering 155 degrees Celsius. And crucially, they have zero piezoelectric effect, meaning physical vibration will not accidentally generate false electrical noise. They pair these up with ultra-precise resistors just to ensure the defense system's calibration is absolutely flawless.
Section 4. Zero Tolerance Forging. Let's look at the process controls.
Of course, a perfect design is completely worthless if it's built poorly, right? And this brings us to some truly sci-fi manufacturing techniques. To make sure those micro cracks we talked about never form, every single circuit board goes through inline 3D X-ray inspection. The total voiding rate in the solder cannot exceed 5%, and no single pad can have a void larger than 1%. If a board fails, the factory system automatically locks the physical track to quarantine the bad part, no exceptions. And for the connectors, they use an automated machine to precisely spray a 10 micrometer layer of Nyogel lubricating grease to stop friction wear. But how do they actually know it's exactly 10 micrometers? They mix a UV fluorescent tracer right into the grease and use an industrial UV camera to verify 100% perfect coverage before that part is allowed to move an inch further down the line.
And finally, Section 5, the ultimate siege. Validation testing. Before any of these inverter units are allowed anywhere near mass production, they have to survive a brutal final boss sequence of validation tests. And I mean punishing. The engineers subject these units to a vicious combination of thermal shock, literally slamming the temperatures from negative 40 to positive 150 degrees Celsius, while simultaneously hitting it with 3-axis random vibrations for 500 hours straight. While it's being shaken and baked, they forcefully drop the power down to 6 volts for 20 milliseconds just to prove those backup capacitors do their job. And the grand finale? They run the motor at a screaming 12,000 RPM at full load and intentionally short-circuit the gate drive power supply to simulate a catastrophic UVLO fault, ensuring the safety systems engage in under 60 milliseconds.
So what does success actually look like after all that? Well, after 500 hours of pure torture, there cannot be a single control signal disconnection lasting longer than 1 microsecond. The electrical contact resistance can only shift by a microscopic 1.2 milliohms. Just to put that into perspective, that is less electrical resistance than a short piece of standard copper wire. And during that high-speed fault injection, the system has to successfully clamp the short-circuit current below 550 amps, protecting the entire system without a single component burning out and with zero permanent damage to the motor magnets.
I want to leave you with this final thought. There's this quote directly from the source material that I think really captures the spirit of this engineering perfectly. I can build a common mode, high-frequency displacement current model to precisely quantify ground bounce noise amplitude under different dV/dt steepness. I love that because it perfectly highlights that this level of engineering is just an ever-evolving battle against physical limits. They are literally building complex mathematical models to predict and tame the chaotic high-frequency noise that naturally wants to tear these systems apart. It makes you look at your EV a little differently, doesn't it? Knowing that this fortress of microsecond defenses is fighting invisible, chaotic battles every single time you press the accelerator? As electric vehicles continue to push the absolute limits of physical hardware, it really begs the question, what invisible forces will engineers have to conquer next? Thanks for joining me on this explainer, and I'll catch you on the next one.